This entire 1U rack-mounted NAS is powered by a ZimaBoard 2, two 12TB drives in RAID 1, and a tiny ESP32 running a live status display. It mirrors the drives, it monitors its own RAID health, and it exposes internal system data through the CasaOS API, which I then pipe into this little OLED display on the front. But this isn't just a plug-and-play NAS build. I designed a custom 3D printed 1U rack enclosure, I built a custom SATA power cable, and I reverse engineered the CasaOS API to pull live RAID stats. In this video, I'll show you how I built it, how it works, and how you can turn a compact board like this into a fully rack-mounted API-driven NAS system. Let's build it. Alright, let's take a closer look at the ZimaBoard 2. Before I open this up, quick disclosure, Icewell sent me this board for free for this build. There was no script, no talking points, just the hardware. And honestly, this board fits the NAS project almost suspiciously well. Now, the packaging itself is pretty minimal, which I actually appreciate. No oversized retail box and no unnecessary plastic, just a sturdy cardboard enclosure that feels functional. Opening it up, everything is neatly laid out inside, and you immediately get a sense that this isn't just another lightweight dev board. First impression, it's heavier than you'd expect, and that weight actually gives it a more server-like feel. This isn't a microcontroller pretending to be a computer, it's a compact x86 machine built to run real workloads. The ZimaBoard 2 is essentially a single board server designed for things like NAS builds, home labs, self-hosted services, or edge deployments. And for what I'm building here, it's going to act as the brain for the entire system. Looking at the front, you've got dual gigabit Ethernet, which is fantastic for a NAS. There are two USB 3 ports, HDMI for direct output and power input. Around the back, you've got the SATA connectivity. And this is the key feature for this build. Native SATA means I can directly attach full-size drives without adapters or USB bridges, which makes it much more appropriate for proper storage applications. Everything is laid out cleanly, nothing feels cramped, and nothing feels like an afterthought. Now, in terms of accessories, you also get a few extra bits in the box. There's the SATA Y cable connector for powering drives, which I'll actually be modifying slightly for my rack design. There's also the PCIe interface, which allows expansion, including NVMe adapters if you want to go that route. You also get the necessary display adapter cable and network cable, so you can get up and running immediately if you want to connect it directly to a monitor. Overall, it's a very practical, no-nonsense package. And for a compact board like this, it packs in exactly the features you'd want if you're building something that's meant to stay on, quietly running in a rack. And in my case, it's about to become the core of a fully custom 1U rack-mounted NAS. So instead of just mounting everything loosely in a rack, I decided to design a proper 19-inch 1U enclosure from scratch, and I designed the entire thing in Onshape. It's a fully structural 3-part system designed to hold the drives, the ZimaBoard, and the monitoring hardware securely inside a standard rack. The rack is printed into 3 main sections. On the left and right we have the drive base, and in the center we have the electronics compartment. Splitting it into 3 parts makes it easier to print, easier to assemble, and much stronger once everything is bolted together. Each outer section is designed to hold a 3.5-inch 12TB drive. Instead of just screwing the drives directly into the frame, I designed removable trays that slide in on integrated rails. You can see here these rails are built directly into the print. The trays slide in from the front, and once inserted, they're fully supported along both sides. That keeps the drive aligned and reduces vibration. Because these are mechanical hard drives, stability matters. The left and right sections are mirrored versions of each other, so the entire rack remains symmetrical. That also keeps airflow and weight distribution balanced across the enclosure. The center section is where all the control hardware lives. Here, I've designed cutouts specifically for the ZimaBoard 2, the ESP32, the OLED display, and 2 5mm LEDs. Everything has a defined mounting position and nothing is just left floating inside. The Zima sits securely in the center, acting as the NAS brain. Next to it is the ESP32, which handles parsing API responses and driving the display. On the front face, we've got the OLED cutout along with 2 LED indicators, one for system status and one for visual feedback. One important detail is these holes running all the way through these 3 sections. These are designed for 5mm threaded rods. Once the rack is assembled and mounted, threaded rods pass through all 3 sections and are tightened down with nuts on either side. This essentially clamps the entire enclosure together, turning 3 printed pieces into one rigid structure. Designing it this way means the drives are supported, the electronics are protected, the entire unit is structurally reinforced, and everything lines up cleanly within a standard 19-inch rack format. Of course, designing it in CAD is one thing, printing it, assembling it, and seeing whether it actually fits, that's the real test. And after many failed prints, I finally had something that I was happy with. Now that all three sections are printed, I need to do a full test fit before installing any of the electronics. The rack is split into a left drive, a right drive, and the center for the electronic section. The first step is just aligning them and making sure the mating surfaces sit flush. The geometry between each section is designed to self-align so there's no guesswork during assembly. Once they're positioned, I slide 5mm threaded rods through the entire chassis. These run from one end to the other and clamp all sections together. When the nuts are tightened down, the structure becomes one rigid frame instead of three separate prints. This is especially important since I'll be holding two 3.5-inch mechanical drives in them. At this stage, I'm just checking for flex or misalignment, and everything feels solid. Next, I'm installing the drive trays. Each tray slides along integrated rails that were modeled directly into the side sections. The tray seats cleanly and sits flush with the front face. The second drive installs the same way, sliding fully into place and aligning evenly with the first. With both drives installed and the frame tightened down, the chassis is structurally complete. Everything lines up as designed and there's no binding or warping between sections. Before installing the threaded rods permanently, I need to cut them down to size. I measure the full length of the assembled chassis, leaving just enough extra on either end for washers and nuts. Once it's marked, I'll cut each rod to match. I'm using an angle grinder for this, which makes quick work of it. After cutting, I clean up the edges slightly so the nuts thread on smoothly, which prevents cross-threading and makes final assembly much easier. With the rods cut to length, they fit exactly within the chassis width, enough thread for tightening without excess sticking out on either side. At this point, the mechanical side of the build is working as intended. Now it's ready for the wiring and electronics. Alright, so the first issue I ran into is the SATA Y cable connector that comes with the ZimaBoard 2. It's included in the box, and electrically it's exactly what we need, but physically it's just too short for this rack layout. With the drives positioned on either side of the chassis, there's no way this cable comfortably reaches both of them. Now the good news is that on the back of the ZimaBoard 2, the power output for the drives uses a standard 4-pin JST connector. So instead of trying to stretch this cable or redesign the layout, I picked up 2 standard SATA power leads that terminate in the same 4-pin JST connector. This gives me the extra length I need to reach both hard drives cleanly. So the plan is simple. I'm going to splice the wiring so that both drive connectors are combined into a single JST connector that plugs directly into the ZimaBoard. To do that, I'll use Wago connectors to join the corresponding power and ground lines. That way I can extend the cable properly, keep the wiring secure, and avoid soldering directly onto the board's original lead. Once everything is matched correctly, 12 volts, 5 volts and ground, the new combined connector should behave exactly like the original Y cable, just longer and better suited for the chassis. Let's put it together and see how it works. For my OLED display, I wanted to pull live system data directly from the NAS. Right now, it's running on a simple breadboard setup, powered by ESP32. During boot, it initializes, connects to the network, and prepares to query the ZimaBoard. Once connected, it begins talking to CasaOS. CasaOS exposes an internal API, but like most APIs, it requires authentication before you can access anything useful. So the first step is logging in. The ESP32 sends a post request to the login endpoint with the configured credentials, your username and password. CasaOS responds with a JSON payload that includes a JSON web token. That token is effectively your session key. Every request after this needs to include it in the authorization header, otherwise the request will be rejected. Once authenticated, the ESP32 makes a second request, this time to the RAID status endpoint. This returns a detailed JSON structure describing the RAID configuration. It includes the RAID level, the state of the array, disk presence, synchronization status, temperature, everything CasaOS knows about the storage layer. But instead of displaying the raw response, the ESP32 parses it. It extracts only the fields that matter for quick diagnostics, things like whether the RAID is healthy, how many disks are active, whether the array is in syncing or degraded mode. That processed data is then formatted into a simple readable layout and written directly to the OLED display. So what we have here is live information coming from the ZimaBoard, authenticated through CasaOS, processed in real time by the ESP32 and rendered on the display. That means that at a glance, without logging into a browser, I can see the health of the RAID array. If a drive fails, if the array starts rebuilding, if something goes out of sync, it shows up here immediately. It's a small display, but it turns the NAS from a silent black box into something that communicates its own status. With both 12TB drives installed, the next step is configuring them as a RAID array. For this build, I'm using RAID 1. RAID 1 is simple as it just mirrors data across both drives. Every file written to the NAS is written to both disks simultaneously. That means that if one drive fails, the other still contains a complete copy of the data. Inside CasaOS, I navigate to the storage section. From there, I select Create Storage. Instead of using the disks independently, I choose the option to combine them into a RAID configuration. Then I select both 12TB drives. For the storage name, I'm calling this array Wolfenstein. Once everything looks correct, I hit Create. At this point, CasaOS begins initializing the array. Under the hood, it's configuring the drives as a mirrored pair. The disks are formatted, metadata is written to both drives, and the RAID structure is established. If the drives already contain data, the system would need to synchronize them. In this case, since they're fresh, the initialization process is straightforward. From this moment forward, any data written to the NAS will be duplicated across both drives automatically. The operating system treats them as a single logical volume. And this is exactly the state information that the ESP32 is monitoring. If you're interested in how the ESP32 communicates with CasaOS and drives the OLED display, I've published everything to GitHub. The repository is called ZimaBoard Monitor. It contains the firmware, the API handling logic, and the display formatting code. You can find the link in the description below. And finally, with everything assembled, wired and configured, it's time to mount it. And now that the assembly is complete, here's the final result. And with that, I have a fully working DIY custom built rack mounted NAS. If you're interested in building something similar, I'll link the firmware, 3D designs and more details in the description. If you've enjoyed the project, don't forget to like and subscribe, and I'll catch you next time.